infinite multiverse foam. In 1980, a physicist named Alan Guth sat down with a stubborn technical problem in Big Bang cosmology and emerged with something he hadn't been looking for. His theory of cosmic inflation, published in Physical Review Letters in 1981, proposed that in the first fraction of a second after the Big Bang, the universe expanded at a rate so violent and so fast that it stretched space itself beyond anything we can meaningfully picture. The theory solved several irritating problems in cosmology almost immediately, but it came with a consequence that Guth and his colleagues didn't fully appreciate at first. One that Soviet-born physicist Andrei Lind would spend the following decade pulling apart and reassembling into something far stranger. Linde's refinement, which he called chaotic inflation and published in 1983, revealed something deeply unsettling buried inside the mathematics. Inflation, once it starts, doesn't stop everywhere at once. Quantum fluctuations, the random probabilistic tremors that govern all matter at the smallest scales, cause inflation to keep going in some regions even as it ends in others. Each region where inflation ends becomes a universe, a bubble of space with its own physical constants, its own laws, its own version of reality. And because the inflating space between bubbles expands faster than light, those universes are permanently, irreversibly sealed from one another. This is what physicists call the eternal inflation model, and its implications for the question of what our universe expands into are immediate and vertiginous. Our universe is not the whole of reality. It is one bubble among a number that may be infinite, nucleating constantly from a churning background of inflating space that never stops producing new realities. The observable universe, all 93 billion light-years of it, is a single soap bubble drifting through a foam that has no edge, no center, and no end. The physical constants in each bubble universe depend on how the quantum fluctuations resolved in that region during inflation. In some bubbles, electrons may have different masses. In others, the strong nuclear force may be calibrated differently, making atoms impossible, making stars impossible, making chemistry and life and thought impossible. Our bubble happens to have the right values. But the eternal inflation framework, championed by physicists including Alexander Vilenkin at Tufts University, suggests this is not special. It is simply the selection effect of being observers in a bubble that permits observation. What the universe is expanding into under this model is a sea of other expansions, a background of inflation that never resolves, endlessly producing new realities that will never interact with ours. We ask where the universe expands into as though the answer must be a place. Eternal inflation suggests it is a process, boundless and unstoppable, and our entire cosmic history is just one moment of resolution within it. Number 9, the quantum foam beneath space itself. In 1955, physicist John Wheeler was working through the implications of combining quantum mechanics with general relativity when he arrived at a description of space that has disturbed physicists ever since. At the smallest meaningful scale of distance, a length now called the Planck length, and measured at 1.616 times 10 to the power of negative 35 meters, space does not behave like space. It writhes. It fluctuates. It boils with energy that has no stable geometry and no fixed structure, a condition Wheeler called quantum foam, and it represents the most violent environment in the known universe. To understand why this matters, it helps to know what physicists mean by the vacuum of space. Empty space is not truly empty. Quantum field theory, confirmed across decades of precision experiments, tells us that every point in space seethes with virtual particles, pairs of matter and antimatter that flicker into existence and annihilate each other in intervals too brief to measure. The Casimir effect, demonstrated experimentally in 1997 by physicist Steve Lamoureux at Los Alamos National Laboratory, proved this directly, showing that two uncharged metal plates, placed close together in a vacuum, are pushed together by the pressure of virtual particles. The void has structure, the void has energy, but at the Planck scale, this becomes something stranger still. Wheeler's calculations suggested that at 10 to the negative 35 meters, space-time itself loses its smooth, continuous character and becomes a churning topology of microgeometries, theorized structures where the curvature of space fluctuates so wildly that the very concepts of here and there lose their meaning. What the universe is expanding into at its most fundamental level may be more of this, a pre-existing substrate of quantum geometry that space itself is crystallizing out of as the universe grows. The energy density of this quantum vacuum, when physicists calculate it from first principles, produces a number that is approximately 10 to the power of 120 times larger than the observed value of dark energy, the force driving the universe's expansion. This discrepancy, sometimes called the worst prediction in the history of physics, was identified formally by Nobel laureate Steven Weinberg in a landmark 1989 paper in Reviews of Modern Physics. Something is canceling almost all of that vacuum energy. We do not know what. The number that remains, the sliver that becomes dark energy, is the force pushing the universe outward into more of this roiling substrate. The universe is not expanding into emptiness. It may be expanding into something far more structured than any matter we know. A substrate so small and so energetic that every cubic centimeter of what we call nothing contains more energy than we can calculate. And our entire cosmos is just the thin, cooled surface of something that has no bottom. Number 8. The higher dimensional bulk. In September 1999, physicists Lisa Randall at Princeton and Raman Sundram at Boston University published 2 papers in Physical Review Letters that offered a radical solution to one of particle physics' most embarrassing problems. Gravity is absurdly weak compared to the other fundamental forces. A small magnet can lift a paperclip against the gravitational pull of the entire Earth. Why? Randall and Sundram's answer required the universe to be something that no human sense can perceive. A thin, 3-dimensional membrane floating inside a higher dimensional space they called the bulk. String theory, the leading candidate for a unified theory of physics, requires either 10 or 11 dimensions to be mathematically consistent. M theory, the framework that encompasses multiple string theories, requires 11. The extra dimensions in most formulations are compactified, curled up so small they are undetectable. But the Randall-Sundram models propose something different. At least one extra dimension could be large, possibly infinite, and gravity would be free to propagate through it, while all other forces remain confined to the surface of our brain, our membrane. This is why gravity is so weak. It is leaking away into a dimension we cannot access. The implications for what the universe expands into are profound. If our cosmos is a 3-dimensional brain within a higher dimensional bulk, then its expansion is lateral movement within a larger architecture. What we experience as the growth of space is, in this picture, the stretching of a membrane through a volume that already exists and that contains more directions than our senses or instruments can process. Other brains may exist nearby in the bulk, separated not by any distance we can measure but by an offset in a direction we have no word for. The Large Hadron Collider at CERN has searched for signatures of extra dimensions, specifically the Kaluza-Klein graviton particles that the Randall-Sundram model predicts. As of 2023, none have been found at the energy scale so far explored, which constrains but does not eliminate the model. The bulk remains a genuine possibility within the framework of established physics. Not a fringe idea, but a serious theoretical structure developed by researchers at some of the world's leading institutions. We look out at the universe expanding in every direction and assume those directions are all there are. But if Randall and Sundram are right, the universe is expanding inside a space that has more room than we can conceive, and whatever else inhabits that bulk has never made itself known. Number 7, the white hole on the other side. Einstein's equations for general relativity are famously indifferent to the direction of time. Feed them a black hole, a region of space where gravity has collapsed matter to infinite density, and the mathematics produces a mirror solution with equal validity, an object that instead of pulling everything in, pushes everything out. A white hole, a region from which matter and energy emerge continuously, and into which nothing can ever fall. For decades after this solution was first formally characterized in the 1960s, most physicists dismissed white holes as mathematical curiosities, artifacts of the equations with no physical reality. Some are no longer so certain. In 2014, physicist Carlo Rovelli at the Centre de Physique Théorique in Marseille, along with collaborator Hal Haggard, published a paper in Physical Review D, proposing that white holes are not just valid solutions, but inevitable endpoints. Within the framework of loop quantum gravity, a leading approach to quantum gravity developed by Rovelli, Lee Smolin, and Abhay Ashtekar from the late 1980s onward, a black hole that has evaporated to its minimum possible size does not vanish. It bounces, the collapse reverses, and the black hole becomes a white hole, spewing back out everything it swallowed across an enormous span of time. This is where the theory becomes genuinely vertiginous. If black holes eventually become white holes, and if the process can work at the scale of an entire universe, then the Big Bang itself may have been a white hole event. A universe somewhere, a parent cosmos we can never access, contained a black hole. That black hole collapsed, hit its quantum minimum, and bounced. What we experience as our Big Bang, that eruption of all matter and energy into existence, 13.8 billion years ago, may be the exhaust of that bounce, the inside of a white hole expanding outward from a singularity that belongs to another universe entirely. Under this model, our universe is not expanding into external space at all. We are the expansion. The outward pressure of the white hole is what we measure as cosmic expansion. And the boundary of our universe, the point beyond the cosmic horizon where space itself recedes faster than light, is the interior surface of a structure whose exterior exists in a cosmos we are physically inside of but can never see. Physicist Nikodem Poplawski at the University of New Haven has developed related models, published from 2010 onward, in which every black hole spawns an interior universe, making our cosmos one of an enormous number nested within parent universes in an infinite hierarchy. We search the sky for what lies beyond the edge of everything, never considering that the edge itself might be a surface, the inside of something that was born from a death in another cosmos. We are not inside the universe. We may be inside a wound in space that belongs to somewhere else entirely. Number 6, the simulation boundary. In May 2003, philosopher Nick Bostrom at Oxford University published a paper in the Philosophical Quarterly that began with disarming clarity and arrived at a conclusion that has unsettled physicists and philosophers ever since. His argument, known as the simulation trilemma, proposed that at least one of three things must be true. Virtually all civilizations go extinct before developing the computational power to simulate conscious minds. Virtually all advanced civilizations choose not to run such simulations, or we are almost certainly living inside one right now. The logic is tight. If even a small fraction of advanced civilizations run simulations of their ancestors, simulated minds will vastly outnumber real ones, making it statistically likely that any given conscious being is simulated. For most of its history, the simulation hypothesis was considered a philosophical curiosity rather than a physical one. That changed in 2012 when physicist Silas Bean and colleagues at the University of Bonn published a paper on AR-Schaff, later developed in further work, suggesting that a simulated universe running on a computational lattice might leave detectable signatures. Specifically, they argued that the GZK limit, the observed cutoff in the energy of cosmic rays at approximately 5 × 10 to the 19 electron volts, first predicted by physicists Greisen, Zatsepin, and Kuzmin in 1966, might be an artifact of the simulation's resolution, the equivalent of pixelation at the edge of a rendered environment. If the universe is computational in nature, its expansion takes on an entirely different character. The universe would not be expanding into space. It would be expanding into allocated memory, computational resources extended by whatever process or entity runs the simulation. What we experience as the creation of new space is, in this framework, the rendering of new regions as the boundary of the simulation moves outward. What lies beyond the current edge of the observable universe may simply be unrendered, waiting to be computed when needed, like terrain in a video game that exists in the code but has not yet been drawn. The simulation hypothesis is not mainstream physics. It is important to say that clearly, but it is taken seriously by researchers who are not naive. Neil deGrasse Tyson at the American Museum of Natural History has stated publicly that the proposition deserves more than dismissal. Max Tegmark at MIT, whose mathematical universe hypothesis proposes that all mathematically consistent structures are physically real, has engaged with it directly in published work. The question of whether physical existence and computational existence are ultimately distinct is not settled. What the simulation boundary implies about cosmic expansion is deeply strange. Every new light year of space that comes into existence as the universe grows may be a calculation being run for the first time, and the question of what the universe expands into becomes, in this frame, a question about the nature of the system running it. Whether that system has limits, whether it can run out of resources, and whether dark energy might be the first sign of computational strain are questions that physics, as currently constituted, cannot answer. Number 5, the cyclic universe, expanding into its own past. In 2001, physicist Paul Steinhardt at Princeton University and Neil Turok, then at Cambridge University, circulated a preprint that challenged one of cosmology's most fundamental assumptions, that the universe had a beginning. Their ekpyrotic model, published in Science in 2002, proposed that the Big Bang was not the start of time but a collision, a periodic crash between two three-dimensional brains drifting through the higher dimensional bulk, repeating on a timescale of perhaps 1 trillion years, endlessly cycling through expansion, cooling, collapse, and rebirth. There was no first moment. There was no creation from nothing. There was only the cycle. The standard model of cosmology, built on general relativity and confirmed by decades of observation, describes a universe with a definite origin, a singularity 13.8 billion years ago from which all space, time, matter, and energy emerged. This picture has extraordinary evidential support, from the cosmic microwave background radiation first detected by Arno Penzias and Robert Wilson at Bell Labs in 1965, to the precise measurements of the Planck satellite mission, whose 2018 data release confirmed the flatness of the universe to within 0.4%. But the origin singularity, the moment before which physics breaks down completely, has always been the model's most uncomfortable feature. The cyclic model offers an alternative. In Steinhardt and Turok's framework, what we call expansion is one phase of an eternal rhythm. The universe expands, matter dilutes, dark energy dominates, and then a slow contraction or brain collision resets the clock. Roger Penrose at the University of Oxford developed an independent cyclic framework called conformal cyclic cosmology, presented in detail in his 2010 book Cycles of Time, which proposes that the universe's far future and its Big Bang origin are conformally equivalent, meaning the geometry of the end of one cosmic cycle is mathematically identical to the beginning of the next. Penrose has claimed to find evidence for this in the cosmic microwave background, specifically concentric rings of anomalously uniform temperature that he argues are echoes of supermassive black hole collisions from a previous cycle. This evidence remains disputed among cosmologists. What makes the cyclic picture particularly haunting is what it implies about what the universe expands into. The answer, in this model, is its own future. The universe expands into conditions that will eventually become the preconditions for its own rebirth. There is no outside. There is no container. There is only the relentless repetition of a process that has no beginning and no planned end, erasing each version of itself completely before producing the next. Every star, every galaxy, every record of this cycle will be obliterated before the next one begins. If the cyclic universe is correct, the most terrifying answer to where the universe expands into is this: nowhere new. It expands into the same space it has always occupied over and over, destroying all memory of what came before, a loop without origin, without exit, and without witness. Number 4, the false vacuum beneath reality. In 1980, physicists Sidney Coleman and Frank DeLucia published a paper in Physical Review D that most people at the time read as an interesting theoretical exercise. The paper described what would happen if the vacuum of space, the lowest energy state of the universe, turned out not to be the lowest possible state. If the universe rested not at the true bottom of its energy landscape, but on a shelf above it, a metastable condition they called the false vacuum, then at any moment anywhere in space, a quantum fluctuation could trigger a transition to the true vacuum below. The consequences, Coleman and DeLucia showed, would be total and instantaneous. And in 2012, we confirmed that this scenario is not merely theoretical. The discovery of the Higgs boson at CERN's Large Hadron Collider on July 4, 2012, was celebrated worldwide as one of the great triumphs of experimental physics. Peter Higgs and Francois Englert received the Nobel Prize in Physics in 2013 for predicting the particle's existence. But the measured mass of the Higgs boson, approximately 125.1 gigaelectron volts, carries a disturbing implication. Calculations published by physicists Giuseppe de Grassi, Stefano De Vita, and colleagues in the Journal of High Energy Physics in 2012, and refined by Dario Butazzo and collaborators in 2013, showed that this mass places our universe's vacuum in a metastable state. The universe is not at the bottom of its energy landscape. It is on a ledge. A bubble of true vacuum, nucleating spontaneously at a single point in space, would expand in every direction at the speed of light. Inside the bubble, the laws of physics would be entirely different. The Higgs field would settle to a lower value, and the mass of every electron and quark in the universe would change. Atoms as we know them would be impossible. Chemistry would be impossible. The bubble wall would be invisible and arrive without any warning whatsoever, because it travels at the same speed as any signal that could announce its approach. From our perspective, one moment the universe would exist. The next moment, the universe would not. The universe is currently expanding into a space that carries this same vulnerability. Every new cubic meter of space that the universe creates as it grows is a new region where the false vacuum persists, a new territory where the transition could spontaneously begin. Physicists, including Joseph Liken at Fermilab and Maria Spiropoulou at Caltech, discussed the metastability implications publicly following the Higgs mass measurement, noting that the lifespan of the current vacuum, while potentially vastly longer than the current age of the universe, is finite. The Coleman-DeLucia framework gives no guarantee. The transition could happen now. It could have already begun somewhere in the observable universe. The universe expands into space that is conditionally real, space whose physical laws are maintained by a field balanced on an energy ledge with no railing and no alarm system, and every new region of space it creates inherits the same precarious condition. We are not building on solid ground. We are laying a floor over an abyss, one quantum fluctuation deep. Number 3, the cosmic horizon, expanding into permanent unknowability. There is a boundary surrounding Earth that no telescope will ever see past, no probe will ever cross, and no signal will ever return from. It is not a wall made of anything. It has no surface, no marker, and no physical presence whatsoever. It is simply the distance at which the expansion of the universe carries space away from us faster than light can travel across it, the point beyond which all information is permanently sealed. Physicists call it the cosmic event horizon, and it currently sits approximately 16 billion light-years away in every direction. What makes it terrifying is not its distance. It is the fact that it is shrinking, and the universe is expanding directly into it. To understand the event horizon, it helps to separate it from a more familiar concept. The observable universe, the region from which light has had time to reach us in the 13.8 billion years since the Big Bang, extends approximately 46.5 billion light-years in radius, a figure calculated rigorously by cosmologists Charles Lineweaver and Tamara Davis in a landmark 2005 paper in Scientific American. The event horizon is different. It is not about what light has reached us from, but about what light will ever be able to reach us from in the future, given the accelerating expansion of space driven by dark energy. The two boundaries are not the same, and the distinction matters enormously. Physicist Lawrence Krauss at Arizona State University and colleague Robert Scherer published a paper in General Relativity and Gravitation in 2007 that described the long-term consequences of this horizon with disturbing precision. In approximately 2 trillion years, all galaxies outside our local group, the cluster of roughly 54 galaxies that includes the Milky Way and Andromeda, will have receded beyond the event horizon. A civilization existing then will look out at a universe that appears to contain only their own galaxy cluster, surrounded by darkness. The cosmic microwave background will have redshifted beyond detection. The expansion of space will be invisible in their data. They will have no evidence that a Big Bang ever occurred, and no physics that would lead them to discover it. The event horizon means that as the universe expands, it does not merely create new space. It creates new space that is, from the moment of its creation, permanently inaccessible to us. Every second, more of physical reality crosses a threshold beyond which the laws of information theory say we can never follow. This is not a technological limitation. It is not a matter of building better telescopes. It is a hard boundary written into the structure of space-time by the combination of general relativity and quantum field theory. The universe expands into regions that are physically real, that contain matter and energy and stars, and perhaps life, but that are sealed from us not by distance but by the geometry of an accelerating space. We are surrounded by an infinity we can never access, growing larger every second, and we will never know what it contains. Number 2, the pre-geometric void, where space has not yet formed. For a century, physicists have lived with an embarrassing crack running through the foundation of their discipline: general relativity. Einstein's theory of gravity, confirmed to extraordinary precision across every scale, from planetary motion to gravitational wave detection, describes space as a smooth, continuous fabric that curves in response to mass and energy. Quantum mechanics, the framework governing particles and fields confirmed across millions of experiments, describes reality as fundamentally discontinuous, probabilistic, and granular at the smallest scales. Both theories work with breathtaking accuracy within their domains. But when physicists attempt to apply them simultaneously, at the Planck scale, the place where gravity and quantum effects are equally important, both break down completely. The crack at the foundation of physics is also, it turns out, a crack in our understanding of what space actually is. Loop quantum gravity, developed from 1988 onward by Carlo Rovelli at Marseille, Lee Smolin at the Perimeter Institute, and Abhay Ashtekar at Penn State, proposes a solution that is more radical than it first appears. Space in this framework is not fundamental. It is not the stage on which physics happens. It is itself a physical quantity, built from discrete units called spin networks, quantized chunks of geometry that combine statistically to produce the smooth space of everyday experience, the way individual water molecules combine to produce the flow of a river. Smooth space-time is an emergent property. It appears at large scales. At small scales, it dissolves. John Wheeler, who coined the term quantum foam and spent the latter part of his career exploring the foundations of physics, proposed in a 1989 paper called Information Physics Quantum: The Search for Links, that physical reality itself might be built from information, that the geometric and material world is what emerges when information is processed, according to specific rules. Gerard T. Hooft at Utrecht University and Leonard Susskind at Stanford University gave this idea a precise form in the holographic principle, developed in 1993 and 1995 respectively, which holds that all the information needed to describe a volume of space is encoded on its two-dimensional boundary surface, like a three-dimensional image projected from a flat plate. If space is emergent, and if what the universe expands into is the pre-geometric substrate from which space crystallizes, then the edge of the universe is not a location. It is a phase boundary, the frontier where the conditions that allow smooth, stable, three-dimensional space have not yet been met, where what lies beyond is not empty space waiting to be filled, but the raw informational or quantum geometric precursor from which space is still forming. What is beyond the boundary of the universe may have no coordinates, no dimensions, no duration, no property that corresponds to anything in human experience or human mathematics. We ask where the universe is expanding into as though the answer must be a place with location and extent. But if space is not fundamental, then the question may be asking for a geography that does not yet exist at the edge of everything, and the universe's expansion is the ongoing process of creating that geography from something that, in any meaningful sense, is not space at all. Number 1, nothing, and why that is the most terrifying answer of all. Every theory in this list assumes there is something for the universe to expand into. Extra dimensions, quantum foam, inflating bubbles, computational substrates, cyclic brains, crystallizing pre-geometry. Each is a creative and often mathematically serious attempt to supply an answer to a question that feels fundamental. If the universe is expanding, what is it expanding into? The question seems unavoidable. Everything we have ever experienced exists inside something else. Rooms have walls. Atmospheres have edges. Solar systems have boundaries. Galaxies are embedded in clusters. The intuition that every container has an outside is so deep, it feels less like an assumption and more like logic itself. But it is an assumption. And the most rigorous physics we have produced in a century of trying says it is wrong. The mathematical framework that governs cosmic expansion was established in 1922 by Russian physicist Alexander Friedmann, who derived expanding universe solutions from Einstein's field equations. Belgian priest and physicist Georges Lemaitre reached the same conclusions independently in 1927. Edwin Hubble confirmed it observationally in 1929, measuring the recession velocities of distant galaxies from Mount Wilson Observatory in California. What all three of them were describing, and what cosmologists have confirmed with increasing precision ever since, is not a universe expanding through space. It is space itself expanding. There is no medium through which the universe moves. There is no pre-existing volume it fills. The expansion of the universe is the growth of space, and space, in general relativity, is not inside anything. Stephen Hawking addressed this directly and repeatedly throughout his career, most accessibly in his 1988 book, A Brief History of Time. Asking what existed before the Big Bang, or what lies outside the universe, he argued, is like asking what lies south of the South Pole. The question sounds meaningful. It uses grammatically correct words, but it contains a false assumption, namely that the structure it asks about has an outside, and so it fails not because the answer is unknown, but because the question is incoherent. James Hartley at the University of California, Santa Barbara, and Hawking formalized this in their No Boundary proposal, published in Physical Review D in 1983, which describes the universe as having no boundary in imaginary time, no edge, no moment of origin that requires a prior state, no outside that requires a container. The Planck satellite mission, whose 2018 data release represents the most precise map of the cosmic microwave background ever produced, confirmed that the universe is spatially flat to within 0.4%. A flat universe, in the language of general relativity, may be infinite in spatial extent. If the universe is infinite, the question of what it expands into is not merely unanswered. It is geometrically meaningless. An infinite thing cannot expand into anything because it already occupies all possible space. What changes during expansion is not the size of the universe, but the distances between points within it. The universe is not a balloon growing inside a room. It is a rubber sheet stretching with no edge and no table beneath it. There is no beneath. We built a civilization on the assumption that everything is inside another thing, that reality is nested containers all the way out, and that the universe must therefore sit inside something larger. The answer that emerges from a century of the most precise and painstaking science humanity has ever conducted is that this assumption, so natural it feels like perception itself, does not hold. There is no outside. There is no beyond. The universe is not a thing in space. It is space. And when we ask what it expands into, we are asking for a place that does not exist, cannot exist, and has never existed. Not because we haven't found it yet, but because the structure of reality offers no room for it. We are not inside something. We are the something. It has no edge. And somehow that absence, not the monsters, not the dimensions, not the bubbles, but the simple, total, mathematically confirmed non-existence of any container whatsoever, is the most vertiginous thing the human mind has ever been